Unit 1.2. So what we have here is an ASCII table. An ASCII stands for American Standard Code for Information Interchange. ASCII. The ASCII table is where we find the keyboard characters, CHR, and we're finding out what their corresponding value is. So you might say value? What do you mean by value? Well, every character on the keyboard actually has a numeric value. That numeric value is the code for that character. So for example, space is the number 32. So if we're focusing on the middle column here, just look at the middle column because all the columns are pretty much the same. The keyboard character is on the right here. I'm going to focus only on these first two. The decimal, which is the number we know, the numbers you've been working with all your life, the regular numbers 32. Then you have a hexadecimal number here, 20, that represents space. We're going to add one more that's not shown here called the binary number, which is going to be using the bits. Again, computer knows bits, and 8 bits make a byte. And what we're trying to do is to show how does the computer see these characters? Well, it sees them as bits, so we have to do what is known as a conversion. We have to convert the decimal values to bits, the binary value. And while we're at it, we're going to also show how to convert the hexadecimal value. So if I take an example like F, uppercase F, the value for it is 70. And we got to convert 70 to its hexadecimal, 46 here. I just shouldn't say 46, I should say 46. And the binary number for 70 as well. So that's what we're going to be working on. Okay, we're going to take these decimal values and convert them. And then I'm going to give you a couple of practice questions after. Ask you to try them and then see if you can come up with the same solution that I show you afterwards. Now, if you take another example, let's say the lowercase v here, which is a 118. We can figure out that decimal value as its hex 76 and also its binary value. So we want to do some conversions. Now you may wonder, why am I doing this? And it's because the computer doesn't know what an F is. It sees the F as the binary representation of the number 70. So you should be wondering, so what happened to the actual number 70? Like, how does it differentiate between that F, 70, and the number 70? But that's where the whole idea of data and data types come in. See, the data itself is represented as a number, but the data also has a type. So let's look back here. In the introduction, we talk about the variable types, primitives. One of them was integer. If we had an integer, 70, so we had an integer variable and we assign 70 to it, then the computer will know, oh, these series of bits in this byte makes up an integer and not the letter F. Okay? So the type, it doesn't matter what type it is. It could be a video. That's all zeros and ones. It could be an image. Pixels, each pixel broken down into zeros and ones. The computer knows bits, and 8 of them make a byte and so on. So we have to convert. So what we're going to do now is just walk through a couple of conversions. And these conversions, we're going to walk through them. I'm going to give you 2 examples, and I'll give you 3 problems to try and see if you can match my solution. So grab a writing utensil. You can use an iPad, you can use pen and paper, whatever you want to use, you can use. I'm going to do that this very next second. Okay, so we have 2 examples. Example 1, example 2. We have F, the ASCII is 70, and we also have the little lowercase v, which ASCII is 118, and we'll work through these 2 and show all 3 bases and their conversions. So, base 10. What does that mean? 10 symbols, 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Base 2, 2 symbols, 0, 1. Those 2 are bits, if you remember. That's why it's called binary here. And then we have the base 16, which is hexadecimal. And that's 16 symbols, 0 through 9, A, B, C, D, E, F. So in converting from one to the other, we're going to use our decimal base 10 as our numbers to go to because we are accustomed to working with these. So 70 is 70. You're going to start off by writing the base raised to the 0. Okay, we're doing base 10, so it's 10 to the 0, 10 to the 1. If we have another digit here, 10 to the second, and 10 to the third, and fourth, and go on. This is 70 because it's 7 times 10 to the 1 plus 0 times 10 to the 0, and that's 70. Let me just make this clear about the 0 exponent. Anything raised to the 0 is 1 except 0. So this is called the ones place. When you go to base 2, what you want to do is write down 8 bits. 8 bits. Every question I give you, you're going to be able to fit in a byte. 8 bits is a byte. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, all the way up to 2 to the 7. And again, you're starting at 0. You want to turn some bits on and some bits off, keeping in this same format in mind, except a different base. We want to add up to get to 70. So 2 to the 6 is on, 2 to the 2 and 2 to the 1. Why? Because 1 times 2 to the 6 plus 1 times 2 to the second plus 1 times 2 to the first gets me 70. Same is true for base 16. It's 16 to the 0, 16 to the 1. You should be getting the pattern now. It doesn't matter which base. It's going to be that base raised to the 0, then the first, then the second, and the third. You got to make sure these numbers that go up here that represents these placeholders here add up to the number you're trying to get. So we're trying to get 70. So 4 times 16 to the first plus 6 times 16 to the 0 is 70. So what does that mean? 70 in base 10 is 70. 70 in base 2 is 0, 1, 0, 0, 0, 1, 1, 0. And 70 in base 16 is 4, 6. Example 2. Now we have 118, 3 digits. So we got 10 to the 0, the first one, 10 to the 1, 10 to the 2. This adds up to 118. Same through for base 2. We set up the same thing here. We just got to figure out which bits to be on or which bits to be off. This is off because 2 to the 7 is 128. That's too big. The remaining bits are on here, these next 3. Okay, and then this one is off, and then the other 2 are on. And then once we add these up, we get 118. 6, 5, 4, 2, and 1. Base 16, same thing, 7 and 6, because 7 times 16 to the first plus 6 times 16 to the 0 is 118. So what we have here is simply the methodology in converting from one base to another, keeping the decimal in mind, okay? Because you're used to this number, you're going to use it as a guide. 3 practice problems, like I said before. So here we go. A practice problem is conversion. Binary number 1101, 1011, converted to decimal and hexadecimal. Hexadecimal number 3F, converted to binary and decimal. And then we have a decimal 98, binary and hex we want to convert to. So grab something to write and solve these 3. You can pause the video right now. All right. So hopefully you had enough time to solve that, because you just have to pause it enough time for you to solve it and come back. Don't need to rush. Let's go to these solutions. So problem 1, I wrote everything down that was given. Okay, this was the binary given. And I figured out which bits are on, included the bits that are on, add these things up to get 219. So my job then, this is the decimal value, is to turn that into a base 16 value. It's dB. Why? Because d times 16 to the first and b times 16 to the 0 turns out to be 13 times 16 to the first plus 11 times 16 to the 0. When you add those up, you get to 19. On the bottom then, I write them all out, saying that this, the original thing that was given to the base 2, these subscripts here is the base, 219 base 10 is equal to dB in base 16. Problem 2, 3F, base 16 given. 16 to the 0 for the F, 16 to the first for the 3. When I add these things up, I got 63. Put my byte down, 8 bits, and put some bits on and some bits off, such that they add up to 63. So the 5th one, 4th, the third exponent, the second, and the first and the 0th exponent was all on. Gets me 63. One thing we want to pay attention to here is if you get a number and it's an odd number in decimal and you're doing a conversion in binary, the last bit could tell you if it's odd or even. If the last bit is on, it's odd. Why? Because this gets me a 1, the ones place. Since all these values are going to be even, when I add a 1 on, it'll make this value odd. That's a little trick to keep in mind there. So 98 is the other number that was given. It's 10 to the 0 for the 8, 10 to the 1st for the 9. When you do the calculations, you get 98. Same thing here. We write out a byte, 8 bits, turn some things on, some things off. 2 to the 6 is on, 2 to the 5th is on, because this is 64, this is 32. Then when we add on this 2 to the 1st, we get 98. And again, like I just said before, this bit is off because 98 is even. And then when I go to base 16, it's 6-2. Don't say 62, say 6-2. Base 16. 16 to the 0 for the 2, 16 to the 1st for the 6. 6 times 16 to the 1st plus 2 times 16 to the 0 gets me 98. These are all equivalent then. This is the binary equivalent. Base 2, 98, base 10, the number that we know, and 62, base 16. If you got these answers, then you're all set to go. If not, you want to rewind, watch what you did, and see if you could find your mistake. And if you don't find your error, if you made one, then just ask when class starts. Or once we're in class, you can ask a question. So, I'm going to say that brings us to the end of conversion, and it certainly brings us to the end of section 1.2.